our next session will be followed as a hands-on session by Mr. Abhushan on convection. So all of you can get ready for the session.
So I hope you enjoyed the lecture on heat transfer in OpenFOAM, uh, the theory lecture. Now it's time to actually do what we are taught, like what you just learned in OpenFOAM. So as you can see, on day two, we only did fluid flow simulation. Now we are going to add heat transfer on top of that fluid flow simulation. In heat transfer in OpenFOAM, there is a different way to do it. There are different solvers for it. If you only are only interested in heat transfer in solid, we will also be doing that. So we have a Laplacian foam session at 1:15 by Krishnakant, but this session is all about convection. So the outline of this session would be on heat transfer solvers that are available in OpenFOAM, and we are going to see how convective heat transfer through a pipe can be done in OpenFOAM, and we are going to use axis symmetric simulation. So yesterday, Professor Manusrita's lecture, you might have learned or saw the wedge geometry. We are going to use that geometry today, and we will be also talking about boundary condition that is applied and what kind of boundary condition are we going to use on the ways side of that axisymmetric mesh. And at the end, I'm going to provide you some assignment that you can do at your own time. So there are different heat transfer solvers available: Laplacian foam, buoyant pimple foam, buoyant simple foam. Since this talk is on convective heat transfer, I'm only providing those solvers that do convection heat transfer problem in OpenFOAM. So first one is buoyant pimple foam. Buoyant pimple foam and buoyant simple foam is quite similar to each other. Only difference being that buoyant pimple foam is a transient solver and buoyant simple foam is a steady state solver. Now, this both of the solvers are for compressible fluid and includes heat transfer, radiation, and so on. Now, CST multi-region foam. CST stands for conjugate heat transfer. So if you have a heat transfer problem where heat is transferred from a fluid region to a solid region and vice versa, then you can use CST multi-region foam. If you want to simulate heat exchangers, such kind of problem, then you can use CST multi-region foam. Now, this is a transient solver, and it also involves buoyant and turbulent fluid flow along with solid heat conduction. Now, since we are going to use buoyant simple form today, this is the file structure that is in the buoyant simple form. So similar to any other cases, we have zero, constant, and system directory. And inside zero directory, you are seeing that there are two extra terms. Those are PRGH and then temperature. So initially there would be only U and P, where it would be stand for velocity and pressure. Now we have one more term, PRGH, and since this problem involves heat transfer, there is a file for temperature as well. And if you see at constant, we have two extra file. Those are thermophysical properties and then G. The G file will give you, if you want to provide gravity in your simulation, you can provide whether you want to provide gravity or not, or the direction of the gravity, you can provide it in your G file. And in thermal physical properties, the properties of your fluid or your solid in your domain, you can provide in the thermophysical properties. Uh, Turbulence properties file is similar as before. You can provide, if you want to use turbulent or laminar, you can provide that in turbulence properties. And what kind of model do you want to use? You want to use K epsilon, K omega, that you can provide in turbulence properties. Okay, now this is the problem that we are going to do simulation of today. Is a convective heat transfer problem through a pipe. So our pipe is about 5 meter long, and initially the section of the pipe that you see in the black color, it is not heated, and we expect the pipe to be fully developed after certain length, and after which we are going to heat the pipe. Now the red section that you're seeing is the section where we heat the pipe, and before that, before this red section on this black section over here, we are going to give adiabatic boundary condition. And here we are going to provide the heat flux or temperature. Now, the properties that we are going to use, uh, the pipe will be of the radius 0.05 meter and the length is 5 meter. And where the fluid that is flowing through the pipe is a air, and we are giving the molecular weight and the density of the air and specific heat along with viscosity and thermal conductivity. These properties will be provided in the file thermophysical properties. And the heat flux at the wall that we're going to provide is 20 watt per meter square, and the inlet fluid temperature is going to be 300 Kelvin. Now, since we're going to simulate a laminar flow, we are keeping the Reynolds number at 500, and we have an empirical relation for entrance length, that is 0.06 times Reynolds number times the characteristic dimension d, which will be 3 meter. So after this 3 meter, at 3.5 meter, we are going to provide this heat flux. So this is the axisymmetric geometry in OpenFOAM. So instead of solving the whole pipe domain, we are only going to solve one part of it. The reason that we can do this is because our solution would be axisymmetric. That means that the in theta direction, so we have a direction. So we have a direction, this is the r direction, and we have a theta direction. And in theta direction, the solution doesn't change at all because the problem itself is axisymmetric, because of which we are able to just simulate a part of the domain that is a wedge shape, and then just say that this solution that we get will be same in the theta direction or azimuthal direction. Again, this is the axisymmetric geometry in OpenFOAM. So the block that we are going to create in block mesh will be of this shape, and it is necessary that the angle of that block should be at 5 or less than 5 degree for our simulation to be accurate.
Excuse
Now,
me, I have a question.
Yes.
Top part should not be curved. Why it is flat?
Yeah.
Means at the top
So-
part should not be curved.
So no need for it to be curved, since this is an approximation. So if you join this small ways, you will end up with a circle. We just assume that uh, the degree is kept less than 5 degree, so that we won't get any error in our solution. We will get error, but that will be very small enough. And we just assume
Okay.
that this assumption
This is the approximation,
yeah,
right?
yeah, it's an
This is-
approximation.
Okay.
Okay. So I want all of you to go to this link bit.ly358 SRMP and then download the folder heat flux. You can just copy it. I'm going to type it in the chat box as well. I'm going to give you guys some time to download the file that I'm going to use. So if you click on that link or you go to that link, you will end up in this OneDrive. And if you click on this download, you will download this heat flux. I'm going to click on it. So it is downloaded. So we'll be using that file later on. So right now you can just we will just carry on with the lecture. So yeah, again, if you click on the download, you will be able to download. You have to extract a zip file. Now, if you download the zip file and extract all the files, and you can either copy it to your run directory, or if you are using VirtualBox, you can just use this command and go to the downloads. However, if you are using WSL, I want you guys to use go to this run directory and then do explorer.exe space dot, and then copy that extracted zip file over there. Or you can just mount your drive and go to the download. If you have confusion right now, don't worry. I'm going to show you how to do that later. So again, this is the buoyant simple form file structure. So let's discuss some of the important part of this file structure. This is the block mesh that we are using to build. So this is how our block mesh is, and we are using two blocks here. So this is our first block, and this is our second block. And for 3.5 meter length, we have one block, and after 1.5 meter, we have the other block. We are using two blocks because in this block we are providing the heat flux or the temperature at the wall. However, in this wall or in this wall of this block, we are providing adiabatic boundary condition, which is why we are using two different blocks. You can, if you want to see how this block mesh stick is made, you can just go to the system and block mesh stick. There you can see. Don't worry about it. We'll see later on as well. Now the boundary condition that we will be providing at the inlet, we are going to provide 0.073 meter per second for Reynolds number of 500, and at this is for velocity. And at the adiabatic wall, we are going to provide no slip boundary condition. And similarly, at the heated wall, we are going to provide no slip boundary condition. And for outlet, we are going to give zero gradient boundary condition. This is for velocity only. And for pressure, we are going to give zero gradient boundary condition everywhere. But at outlet, we are going to fix the pressure at 0 pascal. Now the temperature at the inlet, we are going to give 300 Kelvin, and at the adiabatic wall,
Can you explain the pressure boundary condition? Why this is zero gradient in everywhere? Can you explain a little bit?
so pressure is zero gradient at the wall because at the wall we don't have flow in the normal direction, right? Because this is a
Okay.
wall, it's a no penetrating boundary condition, and we don't have flow in the normal direction. So if there is no flow in the normal direction, that means so for the flow to happen, there must be some pressure gradient, right? If the
Yes.
so if there is no flow, that means the pressure gradient in the normal direction is zero. So at the wall, dp by dx or equals to zero, x by y, whatever. Did you got it?
Okay. Yes. Why at the inlet? Zero gradient.
At the inlet. So at the inlet, we are providing zero gradient because we can do one thing. Either we can give pressure at the inlet or at the outlet. It doesn't matter. Right now, we are providing zero pressure at the outlet. And what OpenFOAM does is during the solving part, it is going to, this is a reference pressure. Since the value of the pressure doesn't matter, but the pressure difference matters. The flow happens because of the pressure difference, delta P, not because of the value of the pressure. So if we are providing 0 PA, during the calculation, the OpenFOAM will provide some higher pressure over here. Let's just assume 5 PA. And for that calculation, we are providing zero gradient at the inlet.
But it should not be zero gradient. Means it is over specified. Means there should be the pressure difference, right, at the inlet. That's why the flow is happening.
Yeah, that's why the flow is happening because of the pressure difference. But we don't know that for the, so there is two way of defining. One is the velocity driven flow and one is the pressure driven flow. So if you were to give pressure here, let's say 5 PA, then you will not be able to give inlet velocity over here. That would be pressure driven flow. So in such case, here you will be providing zero gradient in the pressure, in the velocity boundary condition. Why? Because that velocity will be calculated from the pressure difference that we are giving. Right now, this is a velocity driven flow. So we know what is the velocity. Yeah, just let me explain this. We know that our velocity is 0.073 meter per second. And at our outlet, we are fixing some pressure. It can be 0 or 5. This is just an arbitrary value. You can give it any value. And it will just calculate what pressure that we have to give here so that our flow will maintain this 0.073 velocity at the inlet. Did you got it?
Yes. Yes. Yes.
Yes, there was other, someone wanted to ask me some other question.
Hello, sir.
Yes.
Sir, in the heated wall boundary condition where you have given fixed gradient, uh, so sir, how we will specify the heat flux? Like Q by K. What is K?
So K is the thermal conductivity, Q is the heat flux.
Okay,
Sorry,
sir.
yeah, heat flux.
Okay, sir. Thank you.
Okay. So if you let's go back. Yeah. So Q is the heat flux to the wall, and our thermal conductivity is 0.0242. So what we are going to do is we're going to give temperature gradient, which is Q. If Q equals to dt by dx by k, we know that dt by dx must be equals to Q by k. So we know the value of Q, you know the value of K, and this is how we are going to provide it in our OpenFOAM. So that's why I've written Q by K here. That is dt by dx, fixed gradient. This gradient is of temperature. That is dt by dk. Okay. Now, so the inlet temperature is 300 Kelvin, and at adiabatic wall, we're providing zero gradient. And at the heated wall, we're giving a fixed gradient boundary condition, which is being derived from the heat flux and the thermal conductivity, which I just showed you. And we have zero gradient at the outlet. Now, this is the boundary condition. This is how we provide the boundary condition of temperature in OpenFOAM. So the adiabatic boundary condition is given by type zero gradient. Zero gradient just means that we have zero gradient as the name suggests. And at the heated pipe, we are giving fixed gradient. And at the pipe heated length, we are giving fixed gradient. And the gradient that we are providing is 8 to 6.45, which is being calculated like this. That is 20 divided by 0.024, where 20 is our heat flux and this is our thermal conductivity K. Now, the back and front is of type weights. So type weights is similar to the empty boundary condition. That means we won't do the calculation in the direction of the weights. But since this is a weights, we are providing the weights boundary condition here. So again, this is the boundary condition that is being provided. We have two weights, that is weights patch 1 and weights patch 2. In 2D simulation, you might have noticed that we are giving empty boundary condition. So if it's a 2D simulation here and at this wall, we would be providing empty boundary condition. So this is quite similar to that. This is a weights path. So here we provide, instead of empty, weights in the direction where we don't want to do the calculation. Now, thermophysical properties, it is one of the very important file in our simulation, since it contains the equation that we are going to use, as well as like the parameters or the properties of the fluid that we are defining. So it helps us to construct a fluid thermo model that allows us to specify the thermophysical model. So let's start with this top thing. So this is the thermophysical model for fixed composition. That means there is only one composition in our mixture, and it assumes that, so it is based on density, hence the name rho. The F stands for enthalpy and E stands for entropy. And in the mixture, we are assuming that our mixture is a fixed composition, hence pure mixture. That means there is no reaction happening. Our whatever variables, let's say if we may have water or air in our mixture, we are assuming that there is no reaction between them, and suddenly the water will not change into air or something like that. So hence we are giving pure mixture. And transport property is constant. Transport property is constant. It means that we are assuming the viscosity is constant. Not only viscosity, also the Prandtl number is constant. So if you want to do simulation of blood flow where the viscosity changes with the shear strain or stress, then you may want to provide some other transport properties here. And the thermo is, this assumes that our specific CP and our heat of fusion is constant. It doesn't changes. And lastly, we have sensible internal heat. So internal energy is used in our solution here, and there are two options available. One is sensible and other is absolute internal heat. So if you want to include heat of formation as well, then you have to use absolute. But since we don't want to use heat of formation, we don't have a phase change happening right now, so we are using sensible. So if you want
in
yeah.
Excuse me, in energy section there is one option is sensible enthalpy.
Yeah, there is one more, sensible enthalpy. Yes.
Yeah. So what is the use of sensible internal energy, and what is difference means in sensible enthalpy energy and sensible internal energy in this case?
There is two way to solve any heat transfer problem. So either you can use enthalpy transport equation, or you can use entropy transport equation. So based on that, what you want to use, you can provide it. You will get approximately almost the same answer. However, right now we are providing solving this equation using internal energy.
thermosection also there is H const and E const. So
Yeah, yeah,
when we use the H const and when we will
yeah.
use E const,
Yeah, when you use as constant, you are using internal. When you use E, then you may want to use the entropy.
but you have an idea or scenario when we should use H const and when we should use E const. Any specific thing, because two
So
options and it should have different use cases.
yeah, there are two. Son, it's just that there are two ways to do the same thing. Right now, I cannot think of any problem where you want to use one cases specifically. But in general, like most of the problem that we do, you can go with any route. You'll get almost the same answer with slight changes because of the numerical errors. Okay.
Okay, thank you.
Now, if you go below to the thermophysical properties, you will get to this section where we provide our molecular weight and then equation of state, we provide density, and then we provide CP and HF. HF stands for heat of formation. That means whenever there is change of phase, we need to provide heat formation. Right now, there is no heat formation, so this is just a placeholder right now. And this is the viscosity, and this is the Prandtl number.
Excuse me, molecular weight is going to affect in our simulation, or we can put any number
So right
in
now
this
it,
case?
yeah, right now it doesn't affect because there is no heat, like there is no phase change, and we have only one uh, fluid. This we can use buoyant simple form to simulate different mixer. In such case, you may want to use molecular weight. In only in such case, the molecular weight will affect.
Okay, thank you.
So the commands to run that file is blockmesh, as usual, which meshes our block, and then buoyant simple form, which will run our solver and writes the result in the heatfox folder, and then we can finally visualize using paraform. Uh, Now I think what I'm gonna do is I'm gonna show you guys the actual simulation. So this is the heatflux file that I downloaded. I'm gonna extract it. So it has been extracted. So inside heatflux, I have another heatflux file. Let me open my. So if you forgot any of the command that you used before, what you can do is you can type history, and you can go above and see what commands that you have used before. This is one of the thing I use frequently. So I'm going to use this command cd. This thing I'm going to copy it, and I'm going to paste it in the chat box. This is for the people who are using WSL. Okay. Okay. Now, what this command does is this command will direct you to a directory towards your downloads. Here I'm using regme because in my PC name is regme. Your PC name may be different. It may be something else other. So those you can figure out by going to this PC, and then you can go to users. So here it is regme. In your case, it may be something else. You can just edit that part and put your PC name. So if I press enter here, it will direct me to downloads. Now I am finally in this directory. Yes, anybody wants to ask any
Yes,
question?
sir. I have one doubt, sir, because you are installing the Ubuntu OS, sir. But we are what we are installing? We are installing only the Ubuntu terminal, sir. By you copying this path means I can able to copy only in the Windows 11 path. So can I paste now? It's not opening, sir.
Actually, I didn't understand if you said. So
Okay.
I'm also using WSL only. This is just a terminal. This is not a Ubuntu. You can see this is a Windows, right? I think
Okay.
we are on the same boat here. So this is why I was providing you this command, which I have pasted in the chat box. So what this command does
Okay,
is
sir.
this command will direct you to your download section, download directory. So
If
actually, yeah,
if cell if I am copying means is copy like uh, work C double slash user slash 9163 desktop slash something's coming now, sir. For the error is showing that command not found. C program command is not found.
you're trying to copy something.
Yes, sir. Yesterday I am trying for we are using the Blender directly by using the terminal, sir. But same command I am trying here, sir. It's showing command like that
Okay,
only, sir.
we will fix this issue after this session.
Okay,
Uh,
sir.
you
Thank
can
you.
present your screen. So as I said, right now we are in this directory downloads, and so right now I'm in this file. So if I want to go to my heat flux, all I have to do is cd heat flux. Now I'm in my heat flux, but since this is extracted, I have another heat flux inside my heat flux. Just be careful of that. And now I'm going to go to my actual heat flux by typing the same command. And finally, I'm able to see my zero constant system. Okay, now let's be what is inside the zero. I have TUP and PRGS. I haven't talked about PRGS. PRGS is just the pressure without the hydrostatic component. So if you subtract P minus rho times G, you'll get the PRGS. So it is just a different form of pressure where we have subtracted the hydrostatic term, that is rho times G. Why are we using this? It is because it is convenient. So whenever you are trying to solve heat equation, energy equation, it is convenient to use this modified pressure instead of this pressure that we're using before. On top of that, say if you are using, you are trying to solve some multi-phase problem. So imagine there is water, and above the water there is an air. So if you want to uh, solve or find gradient across this interface between air and water, so there is a certain jump in density, right? The density of water is in 1,000, and the density of air is in terms of 1.22 something. So because of this certain jump, the gradient will also have jump. So we don't want that. It may cause some inconsistency in our solver. So to mitigate that, we are using PRGS in multi-phase flow. Here we are using PRGS just for the convenience. So let me open the T file first. Okay, sorry. So as you can see, I did a mistake. I need to provide the proper directory here. So since it is inside the T file, yeah, there is row GH also. Did I say only row G? It is supposed to be row GH. Okay. So since it is inside 0, I am providing the path 0 as well here. So now, okay, this is my T file that is inside 0. It contains boundary condition for T. So initially, we are going to give uniform one boundary. It means that when our simulation starts, the whole field will be, the whole temperature of my domain will be 1. So you might have noticed that in pressure and velocity, we will provide 0, but now we are giving it 1. Why? Because if you give temperature at 0, our solution will not solve. It's like dividing 0 by 0. So this won't work. This is an absolute temperature. So we need to give some value, any value that is greater than 0. Hence, right now we are giving just 1. And this is the inlet. At inlet, we are giving 300 Kelvin, and it is uniform. And at outlet, we are providing 0 gradient boundary condition. And at adiabatic part of the wall, we are giving 0 gradient. And similarly, as I showed you in my presentation, at the heated section, we are giving fixed gradient, and the gradient is calculated like this, 82.645. This is the temperature gradient, and it is being calculated by dividing Q with the thermal conductivity K. And at the back and front, which is our wedge in this case, we are giving wedge boundary condition. Now let's see the P. So here we actually don't need to provide any boundary condition for P. This is not even necessary. Without the P file, our simulation will run, but we would like to see the actual pressure when we try to visualize our simulation. So the pressure P is being calculated. So it will be calculated based on the PRGS value that is being actually solved in our equation. So I said, right, PRGS equals P minus rho times G times H. So PRGH equals to P minus rho times G times H. And Now we know that PRGS using rho, G, and H, we are going to find out P. This is how this calculated thing is being done. So we are giving calculated boundary condition in all the patches except for back and front, which is our wedge patch. I'm just going to remove it. And okay, now we are going to see velocity. So at inlet, we are providing fixed value, and that value is 0.073. Be careful while providing this uniform. Since this is a vector, I'm giving my velocity in the x direction. This depends on your mesh, how you have meshed your geometry. If your inlet is in x direction, you need to give it in x direction. If your inlet is in y direction, you need to give in y direction. Now at outlet, we are giving zero gradient boundary condition, and at pipe adiabatic and pipe heated, which is the wall, we are providing no slip boundary condition. And similarly to other cases at back and front, we are giving width boundary condition. Okay, now let's see the modified pressure. So initially at inlet, we would be giving zero graded boundary condition if it was just a P folder, but right now we are giving fixed flux. So what does this fixed flux pressure do? It is similar to zero gradient boundary condition, but it takes in account of the other body forces, say gravity force. Right now, our problem doesn't involve body forces like gravity, but if it were to involve, then it takes care of that as well. So that is the difference between just a zero gradient boundary condition and fixed flux pressure. And at the outlet, we are giving PRGS pressure. So before we would provide some pressure at the boundary condition, pressure equals to 0, but this is PRGS, this is not P. So we need to calculate PRGS based on the value of P that is being provided. So at here, we are providing the value of P, which is uniform 0. So based on the value that we have provided, it is going to find out the PRGS value using the same equation P minus rho times G times H. So using this, it is going to find out the PRGS, and it is going to give that value at the outlet. And at adiabatic, again, fixed flux pressure. This is similar to zero gradient, as I pointed out. And same at the pipe heated, these two are just the walls. And at back and front, we have wedge. Let me clear the screen. Now that we have gone through all those files at the P, let's look at the constant. So in constant, we have G, thermophysical properties and turbulence properties. Let's look at G first. Here we are providing our direction of gravity. We have neglected gravity for our problem. That's why the value is just 0, 0, 0. If you want to provide gravity, let's say in Z direction, you can do so by giving here 9.8. But right now we are not providing any gravity. So let's look at the thermophysical properties. This is the most important file. So as I saw in my presentation, this is how our thermophysical file is. So this is a thermophysical model for fixed composition that is based on density. And we are giving pure mixture as a mixture. That means there is no reaction that is happening in our mixture. If you had like two different composition in our mixture, let's say carbon dioxide and then air, there is no reaction between them. But here we have only one mixture, that is air, so we don't need to worry about anything. And in transport, we are giving constant transport. That means our viscosity and Prandtl number is constant. Like I said, say if your viscosity depends on temperature, or if your viscosity depends, if you have a non-Newtonian fluid, then you can just change this parameter. There are different models that is available in OpenFOAM. We can give that over here. And in thermo, we are using H constant. So it assumes that our specific heat is constant and heat of fusion is also constant. And equation of state, we are giving rho constant. I think I forgot to talk about equation of state. So in equation of state, we can provide different parameters. So rho constant assumes that our density is constant. There are other parameters that you can apply, like Bosnian approximation, and the one where the temperature depends on some polynomial expression. And species in species, it thus means that it specifies the composition of each constituent, like number of moles, such kind of thing is used here. So because we have used species in here, we need to only provide molecular weight. And these are just the properties of our mixer. So molecular weight is 28.9, this is of air, and density is 1.225. We are using constant density here in our equation state. If you were to use Boyce's approximation, then we would also need to provide rho, and along with the rho, the temperature and the value of beta over here. And in thermodynamics, we are providing Cp, specific heat, and then heat of formation, which is 0 in our case. And this is the viscosity, and this is the Prandtl number. Now, let's look at our turbulence properties. So since our simulation is laminar, there is nothing to it. It is just laminar. We need not to write any other dictionary. Even if we wrote any other dictionary for our turbulence, it will just ignore it. So let's see what is inside our system. So as usual, we have control dick, every skin, and every solution. Let's see how our block mesh is done. So this is the vertices that we are providing. Just remember the wedge shape figure that was shown to you before, that had two different blocks. So this is the first block where we have adiabatic boundary condition at the wall, and this is the second block where we are providing flux condition. And we are not giving any curve edges. That's why this is empty. So this is how the inlet is defined. So one may notice that how to create a wedge. So previously there would be 4 different vertices for one face, but now we have only 3. So you can just repeat the value where the wedge happens. Like at the axis of the wedge, we have 0 and then 3. So you just have to repeat it. And these are the boundaries: inlet, outlet, pipe adiabatic, pipe heated. We are just giving the numbering of the face in our boundary, and we are not using any merge patch space. So now that it's clear, let's run our simulation. So to run our simulation, first I'm going to do block mesh, which will mesh my geometry. Okay, I have not sourced my OpenFOAM. I have multiple versions of OpenFOAM in my system. So if I do OF9, it will actually load OpenFOAM 9 in my system. You don't need to do that if you have only one version of OpenFOAM. So now that I block mesh, it has meshed my geometry. Now I'm gonna prompt Fluent simple form. It should run my solver. This should take a while because we are solving multiple equation here. We have velocity, pressure, and then energy equation. So as you can see, here we have Ux, Uy, Uz, and E. We have E because in our thermophysical properties, we had given sensible internal energy, and E stands for internal energy. If you were to given sensible enthalpy, then it would be H here. That means we will be solving energy equation based on the enthalpy. So it is still being solved. Let's just wait for a while. Someone is asking why the value of G is 0, 0, 0. We are not considering gravity at this in our simulation right now. How to pause? You can just scroll your mouse. If you scroll your mouse, it will pause. And if you want to continue, just press enter. Okay, our simulation has ended, and let's view our result. If you are using VirtualBox, you can just view it using Parafoam, but now we are using WSL, so let's do some extra work. So I'm creating a dummy file towards result.foam. If I do that, and if I type ls, now I'll have this file result.foam. this this can be used. This can be opened by Paraview to view our simulation result. So I'm going to do explorer.exe space dot. This will open my directory in File Explorer. So as you can see, I am inside my download heat flux and heat flux. So this is the dummy file that I created, and I'm going to click on it, open it. I'm going to click on apply. So this is the pressure. Right now we are at 100 iteration or 100 time step. I'm going to view the latest time step, and this is my pressure. If I want to view velocity, this is how my velocity is. So as you can see here, the boundary layer is developing, and somewhere in between, that is around 3 meters, this developing boundary layer becomes constant, and we say that our flow is fully developed. Let's see at temperature. So as you can see, the temperature is 300 because supplied 300 over here. The blue is 300, and since here we have adiabatic boundary condition, there is no change in temperature. And finally, after 3.5 meter, we are providing heat flux, because of which our temperature at the wall changes, and we have temperature boundary layer along the wall. Now, if you want to visualize the plot of temperature or velocity.
Sir, can I ask one question?
Yes.
Sir, when you were showing the pressure, the values were very little. So these were not absolute pressure. They were relative pressure because atmospheric pressure is 10 to the power of 5 pascals.
This is indeed an absolute, I would say, absolute pressure. But here it doesn't matter the value of pressure. So you want to say that the value of pressure is very less, right?
Yes,
That
sir.
is because at the boundary condition, if you have noticed at the outlet, we had given 0 pressure, right? You remember
Okay,
that?
sir.
So based on
Okay,
that,
sir.
it is calculating the inlet pressure. So
Okay,
the
sir.
value of the pressure doesn't matter. If I can provide 100 in place of 0, and I would get the same result. It's just that my value at the outlet will be 100 plus whatever this value over here is,
Okay, sir.
around 200 something.
Okay, thank you, sir.
Okay. And this is the PRGH. This is the modified pressure that was being calculated. But since our case, we are ignoring gravity, our PRGH and P is same. That's why you see no changes between. And again, so this is the temperature. So I was going to show you guys how we can plot our value of temperature velocity profile at any given length. So first you have to click on this plot over line. And instead of just typing 0.1 and 0.2, I want my line to be aligned. So I'm just going to click y-axis. Why I'm going to click y-axis? You can see the axis direction here. So this is y. So I'm going to click on y-axis. And my line is somewhere over here. I want it to be somewhere over here. Let's type 5 meters since my pipe is a 5 meter length. So as you can see, the line that I'm going to plot across is over here. I'm going to click on apply. So this is giving me different variable. We have P, PRGS, T, and U magnitude. Some of the values are very high, some of very less, because of which we cannot get any information. So what I'm going to do is go over here at my left and series parameters, and then I'm going to click on this all, and I'm going to uncheck that again so that I don't have any values left. So one by one, I'm going to click on the parameters that is of my interest. So let's first see the temperature. So this is how my temperature is changing along my radial direction. So initially at the 0, we have 304. 0 means at the center, we have 300 Kelvin, 304 Kelvin, and it slowly increases to 330 Kelvin. Let's see the U magnitude, that is velocity. So this is how my velocity is. So my velocity would be a parabolic profile. And since this is axisymmetric case, I'm only able to see half of that parabolic profile. So at center, I have my maximum velocity, which is 0.143719, and it is parabolic in profile. Now let's see pressure. So seeing pressure doesn't make much sense in this direction. It would make sense if you were to see it in the this Z direction. Sorry, in this case it is X direction. So I'm just going to click on X and click on apply. So where am I at? Okay. This is my point 1. I want it to be a 0. I want to see. Okay, I'm gonna delete it and I'm gonna plot over line again. So this is how my pressure pressure profile develops across the line. So initially at the entrance, my pressure is very high. That is 0.0249. It may not be high, but it is just larger than my 0. So what we have to look is the pressure difference, not the absolute value of pressure, as I pointed out before. So at the outlet, the pressure is 0, as we defined in our boundary condition. And based on that, the pressure boundary condition at the inlet was given 0 gradient. And based on this value of pressure, it is going to calculate the pressure in the inlet and throughout my domain, so that it will maintain that flow of 0.07 meter per second around that. So this is how you simulate convective heat transfer through a pipe.
Sir, I have one question, sir.
Yeah, you can ask me a question. Yes.
Sir, sometimes our geometry is not well oriented in XYZ direction. So at that time, sir, we want to plot along any line for my desired variable. Suppose that line is inclined. So how can I draw in paraform, sir? Can you show, sir?
Yeah, I'm going to show that to you. It is best that you make your geometry so that it is
always sir,
inclined.
Just like, sir, we are using in full band, sir, probe, we can using probe for detect the point. So like that, can I use here, sir? Any option?
Sorry, I didn't get your question. Just like in
sir,
what?
In case of CFD post, sir, in full band.
Okay.
Sir, at that place, sir, we are using probe for detecting that point and drawing the line where we want to plot that our desired variable. So how can I do here, sir? Is there any option? So like we want to draw inclined line. Is there any option, sir?
Yeah, there's an option to draw an inclined line. So say I'm going to delete this. I'm going to do a plot over line.
So because I don't know the dimension points, the location of the points, but randomly
you need to know the location of the point for that. But even though you don't know, there's a approximate thing that we can do. We can just drag this here. So if your orientation of your geometry is according to this, it will only change in X and Y direction. It won't change in the direction that is perpendicular to you. So as you can see, when I drag this, here it is also changing. So the value of Z here is close to 0, so it is not changing. So let's say I want to plot across this line that is not oriented to any of the axis. Okay, you can just make it 0 and you can click on apply. So this way also you can.
Like, it's hit and trial like that, man.
Yeah, it's a hit and trial, but it's not a hit and trial, because if you are making the geometry by yourself, you know the value of what you want to know. Like, you know, where is my length, where is my edges, right?
All that is the okay. That is the defined thing, sir. Suppose we want to draw at that wall is curved. So at that time, I don't know each and every coordinate of that length.
Okay.
So at that time, it's difficult to draw here, I think.
Yeah, at that time it's difficult to draw. You just have to assume.
In case of CFD post, it's easy, sir.
Okay.
So that's why I'm questioning.
Okay, it's okay. It looks like hit and trial, but if you know your geometry very well, I think you should be able to do it. And okay. I'm just going to present my another window over here. So we were here last time, and this is the profile that we got, constant wall heat flux. Actually, this is not from the ParaView. This was extracted from the ParaView, and then it was post-processed in Excel. You can use LibreOffice or any software that handles tables to calculate this. So say if you want to extract this parameters, say 5 and then.
Hello, sir.
Yeah.
Yeah, I have a general question. Actually, I was using OpenFOAM 10 version, okay, and I ran your solver.
Okay.
solver over there. So the thing was that there is no buoyant simple form over there. It has been replaced by just buoyant form simple a general solver. Okay. Now the same code which you have provided, I'm not able to solve using this particular solver in the OpenFOAM 10 version. This brings me to the general question: if we have any case files which we got from GitHub or generally anything, and we are means we want to update it as regarding as per to our OpenFOAM version. So what changes we need to do for that?
It depends on the new version. So you need to keep track of what is different in different version for that. So generally from version to version, there is not much different, but in OpenFOAM 10, they have done some huge changes. So I think what could be the issue is the thermophysical properties file, the name of the file, any of this file could be different in your OpenFOAM version 10. They might have changed the name. That could be the issue, along with the name of the solver. But generally, from one version to another version, there is not much different. There may be a new solver that may be available in other version, but most of the time they try to adhere to the standard that was maintained before.
So suppose in my case, I am getting this error when I try to run using buoyant form. Keyword pimple is undefined in dictionary home slash my run directory for the open form slash heatflux slash system slash FV solutions. So do I need to change something in the FV solution itself?
Yeah, that means there is something wrong with the API solution. Instead of Pimple, it may have some other name in OpenFOAM 10. That could be the thing. If you have trouble, this kind of trouble, what you can do is just copy paste that error that you get in your any browser. And we have a very good community with OpenFOAM and in CFD online that we mostly use. The problem that you have faced might have also been faced by some other people, and they will post the same problem in CFD online. You can go there and people will be discussing in that CFD online how to solve that problem. Even if you don't find, say, your particular problem, you can post it on CFD online. You have to create an account for that. You can create and post on your problem, and I'm sure there will be hundreds of people trying to solve your problem. So we have a very good community in OpenFOAM. So if you have a particular problem, you'll be very easily able to solve it.
Okay, sir. Thank you. Fine.
Okay. So as I was saying, right now I did a plot, and now if I want to extract this plot, I can just click on this save data. So what it does, it allows me to save the plot that I did in Excel sheet or in Office Libre. So I'm just gonna make some data file, click on OK. So I can select the precision, the number of digit after the decimal, how precise I want my data to be. So I can click on OK. So after this, in my heat flux, I will have one more file data. So either using Access or Excel or Libre, you can post process your data from here also. So this was done by doing the same. So I calculated wall heat flux, and this is the result of that. And this is the non-dimensional velocity profile. And we have a theoretical non-dimensional velocity profile, y equals to 1 minus x square. And this is the one that is generated by OpenFOAM. You may notice that there is some difference or deviation at my wall. This is because I have not used a proper expansion ratio in my wall, so that the number of mesh in the wall is much less or much closer. So if I were to use expansion ratio and make such that near my wall, the number of mesh is much fine than the one in my other, I would be able to eliminate this. And this is an assignment problem. So right now we wasted much of our geometry to provide parabolic inlet profile. Let me go back to our geometry. So in our geometry, from here to here, we are actually doing nothing. We are just letting our flow develop to a fully developed profile. So this is how long? This is 3.5 meter long, but our heat simulation is only being done at 1.5 meter. So 3.5 meter of our domain length is being just wasted to provide parabolic boundary or parabolic flow velocity condition. So instead of doing simulation in this part, what we can do is we can provide parabolic inlet profile directly at the inlet. So this is about that. This is one assignment, parabolic inlet. So we are gonna give parabolic inlet velocity profile directly at the inlet, and we only have to simulate 1.5 meter of our pipe length for that. And if for parabolic inlet velocity, we will not need the other block that was here before. So we don't need this thing. We can just will ignore, and only the second block that was used can be utilized. And this is the code to give parabolic inlet velocity. Let me see what is happening here. Previously, there would be an inlet, and then type would be some fixed value, and then value will give uniform some value. But now we have to code it, and we are using coded fixed value for this thing. So as the type, we are going to give coded fixed value, and this value, we are going to give some value uniform 00. This is just a placeholder. It won't do anything here. And we are gonna name our velocity profile as parabolic velocity, and this is the actual code that gives the parabolic inlet velocity profile. So we're gonna type code and has this bracket, and this will open C++. This will allow us to code our inlet velocity using C++. So FP path at boundary. So from here we are getting all the mesh elements in our mesh using this command paths. And when we do boundary paths.cf, we are actually getting the position of that mesh x, y, and z. So now the CF contains the values of x, y, z of each of these mesh. So if we have different mesh in our domain, it will just give us the value each x, y, z location of the mesh. So if you want to find out the value of y or x or z, what we can do is CF bracket face I dot y. So dot y bracket will give us the value of the y of that particular mesh. And this is the scalar variable that we're using. R stands for the radius of our pipe, and Umax is the maximum velocity that we are going to provide to our parabolic inlet profile. That means if this is a parabolic profile, here the value of U is 0.146 at the middle. Now we are going to loop through all these faces, like all the mesh in our faces. This is that loop for all, and we are going to give a scalar value R, in which we are going to give the value of y coordinate. So CF face I dot y will give the value of the y coordinate. And finally, here we are providing the value of velocity. So what is this vector? Velocity we are giving as a vector. So this is for y, and this is for z. Now this may look familiar to you. So if I were to write it, it would look like this: u times 1 minus r by r square. This is the expression for parabolic profile in a pipe flow. This is that. So this is how you give that profile. So this r it is getting from here, and this r is a constant that is defined over here. So like this, using this expression, it is giving the velocity as a vector. So this is the assignment problem, and you can click on this to get that assignment. I'm gonna copy paste that in the chat. You can do it at your own time when you are free. And this is the non-dimensional velocity profile that you get by using parabolic inlet velocity. And same at 1.4 meter temperature profile. And finally, instead of providing fixed gradient, right now in our simulation, in our heated pipe section, we provided fixed gradient, that is a temperature gradient. We could also provide temperature of the wall. So if you want to provide temperature of the wall, this is how you do it. Pipe heated, type fixed value, and then you give the value of the temperature, that is 310 Kelvin. And like I said, in equation of state, you can provide different parameters. The one that we used currently was rho constant. That means we assume the density is constant. It doesn't changes with temperature. The other parameters that can be used are perfect gas. So based on this equation, value of pressure and temperature, it is going to calculate density. This will be important for density driven flow. And you can also assume perfect fluid. So instead of perfect gas, this is for perfect fluid. This is for gas and this is for fluid. That is the only difference. And this is a Boyce approximation. In Boyce approximation, what we do is we assume that only density is dependent on time, while other parameters in our other properties of our fluid doesn't change with time. Sorry, with temperature, not time. And other is icopolynomial. That is density is a function of temperature. It is almost same as Boyce approximation. Here also we say that other parameters doesn't depend on temperature, only density depends on temperature, and that dependence is based on this some function that is a polynomial function. So thank you. My session has ended here. If you have any question, you can ask us.
Sir, in the heat flux, you provided fixed gradient.
Yeah.
Sir, I think there is another way providing heat flux directly without dividing by thermal conductivity. The name of that boundary condition is external wall heat flux temperature.
Yeah,
So
that
am
also
I
we can do because there is information. So in our thermophysical properties, we have provided information of thermal conductivity. So if you use that, OpenFOAM will automatically calculate your heat flux based on that. Temperature
okay?
gradient or heat flux based on that. Yeah.
Okay, thank you.
Okay, so should we move on to the next session, Abhushan?
Yeah, I think we're running out of time, right? So.
Yeah.